In this section, I'm going to talk about optimality conditions and the method of Lagrange multipliers in order to solve convex optimization problems. So let me start with an important result. Let f be an extended real valued convex functions. And let x bar be a point in the domain of the function. Then we see the following result. F has an absolute minimum at x bar, even only if f has a local minimum at x bar. Okay, and let me recall the concept of local minima. So remember that f has a local minimum at x bar if there exists delta greater than 0 such that f of x is greater than or equal to f of x bar, and this is true for all x in the ball with center at x bar and radius delta. Okay, and recall that f has a global minimum at x bar if this inequality is satisfied for all x in Rn. And obviously, if f has an absolute minimum at x bar, then f has a local minimum at x bar. And under the convexity of the function f, we can prove that the converse is also true. Okay, so let me go ahead and give the detailed proof of this theorem. So it suffices to prove that the converse is satisfied. Okay, so suppose that f has a local minimum at x bar. Then there exists delta greater than 0 such that f of x, we just write f of x bar is less than or equal to f of x, and this is true for all x in the ball with center at x bar and radius delta. Okay. Now let us fix any u in Rn. Fix any then we can find t that is greater than 0 and less than 1 such that x bar plus t times u minus x bar, and this is just t of times u plus 1 minus t times x bar, and this is in the ball with center at x bar and radius delta. Okay, so this is true because this approaches 0 as t approaches 0. Okay, so then as we see from this inequality, f of x bar is less than or equal to f of this element x, which is f of tu plus 1 minus t times x bar. So by the convexity of the function f, this is less than or equal to t times f of u plus 1 minus t times f of x bar. And this can be written as f of x bar plus t times f of u minus f of x bar. Okay? Now here we can simplify f of x bar from both sides and obtain the following. Thus 0 is less than or equal to t times f of u minus f of x bar. And from here, we will see that by dividing both sides by t, we have not f of u, 0 is less than or equal to f of u minus f of x bar. And so f of x bar is less than or equal to f of u. Okay? And this is true for any u in Rn. Therefore, x bar is an absolute minimizer of f. And equivalently, f has an absolute minimizer at x bar. So we have showed that if f has a local minimum at x bar, then f has an absolute minimum at x bar. Now we will focus on the following optimization problem. Minimize f of x subject to x in omega, where f is a convex function from Rn to R. To make the presentation simple, again, we assume that f has real values. And omega is a non-empty convex set. So in this situation, we say that P here is a convex optimization problem. Okay, again, f here is a convex function, and omega, the constraint set, is a convex set. Therefore, we say that f is a convex optimization problem. And as we see earlier, so for a convex function, that function has an absolute minimizer, absolute minimum at x bar if and only if it has a local minimum at x bar. So we do not distinguish between local optimal solutions or global optimal solutions of convex optimization problems in what follows. Okay, so now let me prove a very, very important theorem that involves the optimality conditions for problem P. Consider problem P. Let x bar be an element of omega. In this case, again, we say that x bar is a feasible solution of the problem. Okay, then x bar is an optimal solution of P if and only if 0 belongs to the subdifferential of f at x bar plus the normal cone to the set, the constraint set omega at x bar. Okay, so the proof of this theorem is really, really simple. So we have the following. X bar is an optimal solution of P if and only if x bar is an absolute minimizer of the function g given by g of x is equal to f of x plus the indicator function associated with omega of x. And this is known from the previous lecture. Okay, so and this is true if and only if by the Fermat subdifferential sum rule, x bar is an absolute minimizer of a convex function if and only if 0 belongs to the subdifferential of that function at x bar. Okay, this is called the Fermat subdifferential Fermat's rule. And the proof of this is very, very simple. We can prove by writing down the definition of what it means by 0 is in this subdifferential. And I believed that I already proved the result earlier. Okay, so this is true if and only if 0 belongs to the subdifferential of g at x bar. Note that x bar is the sum of two convex functions. Now here this is an extended real value function, and this is a real value convex function. And as you know, the function f here has real values, so it's continuous. Okay, in particular, it's continuous at any point of omega. So then we can apply the subdifferential sum rule and obtain this. This is equal to the subdifferential of f at x bar plus the subdifferential of the indicator function associated with omega at x bar. Okay, and we already proved earlier that this is just the subdifferential of f at x bar plus the normal cone to omega at x bar. So it is well known that the subdifferential of the indicator function associated with omega at x bar is equal to the normal cone to omega at x bar, and therefore we obtain this result. Okay, now I'm going to present another corollary. Consider problem P, in which omega is the following set, is the set of all x in Rn, such that A times x is equal to B, where A is an m by n matrix and B is a vector in Rm. Okay, let x bar in be an element of omega. Okay, then x bar is an optimal solution of P if and only if 0 belongs to the subdifferential of f at x bar plus A transpose of Rm. Okay? So the proof of this theorem, this corollary, is very, very simple. So from the result we got earlier, we see that x bar is an optimal solution of P if and only if 0 belongs to the sum of the subdifferential of f at x bar and the normal cone to the set omega at x bar. And here x bar is given by this formula, and therefore we can prove that the normal cone to the set omega at x bar is actually A transpose of Rm. So this set can be written as A transpose times lambda, where lambda runs in Rm. Okay. So here, this is the case where the set omega here is an affine set. Okay. In the next lecture, we're gonna talk about the method of Lagrange multipliers to solve optimization problems in which the constraint set omega is defined by convex functions.